Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine, just for a second, that you are standing outside.
Okay.
Like, on a perfectly clear, perfectly dark night. You look up at the night sky and you see the familiar constellations.
Is that the usual stuff?
Yeah, just the dusting of the Milky Way, the quiet, ancient light of billions of stars. And then,
Nowhere.
exactly, without any warning, a single point of light in that sky just suddenly ignites.
Oh, yeah.
And it doesn't just twinkle or get a little brighter. It flares up with such absolute, overwhelming violence that this one single star outshines everything else around it.
It's hard to even picture.
It is. I mean, in fact, it outshines the billions of other stars in its entire host galaxy combined.
Which is just, it is a scale of brightness that the human brain really, truly struggles to comprehend.
Right.
Because when we think of something bright, we think of, I don't know, a spotlight or maybe staring directly at our own sun.
Sure, yeah.
But we are talking about a single, solitary stellar object broadcasting so much luminous energy that it just dwarfs a metropolis of hundreds of billions of suns.
Hundreds of billions.
Yeah, the energy output completely breaks all conventional models of stellar physics.
And I think the wildest part about this is this isn't some thought experiment.
No, it's very real.
This actually happened on May 23, 2017, in a barred spiral galaxy known as NGC 3191.
Which, if you're looking for it, sits right in the constellation Ursa Major.
Right. And just to give you a sense of the neighborhood we're talking about here, this galaxy is located 440 million light years away from Earth.
That's a staggering distance.
440 million. So if you think about it, the star actually detonated 440 million years ago.
During the Paleozoic era here on Earth.
Exactly, like before dinosaurs. And the light from that singular, incredibly violent event just kept traveling and finally washed over our planet on a random Tuesday in 2017.
And when it did arrive, that initial surge of photons was actually caught by the European Space Agency's Gaia mission.
Okay, Gaia, right.
Yeah, and they cataloged it as SN 2017 GM.
That's your name.
Right. Astronomers love their acronyms. But they classified it as a superluminous supernova.
Which means it's one of the big ones.
Exactly. And remarkably, even at, 440 million light years away, it remains one of the closest explosions of its particular extreme type that we've ever recorded.
Which is lucky for us because today we are exploring a monumental recent breakthrough in astrophysics regarding this exact event.
It's a huge deal in the community.
The mission here is to understand the very first clear, definitive detection of gamma rays from a superluminous supernova.
Using NASA's Fermi Gamma-ray Space Telescope.
Right, using Fermi. And by analyzing this specific signal, scientists have essentially peered straight through the dense, explosive wreckage to uncover the hidden, supercharged engine that powers the absolute brightest stellar explosions in the entire universe.
It's incredible.
We are talking about cosmic machinery on a level that is, frankly, terrifying.
It really is. And to appreciate the magnitude of peering into that engine, we should probably briefly touch on the baseline of stellar death, right?
Yeah, let's set the stage.
Just to understand how anomalous SN 2017 Gemeter really is. So we all know the standard core collapse model.
Or at least the textbook version of it.
Right. A star vastly more massive than our sun burns through its nuclear fuel, the outward pressure of fusion stops, and gravity just takes over in an instant.
Well, gravity's always trying to crush the star, right?
Exactly. It's a constant battle, and when fusion stops, gravity wins. The core implodes, the outer layers rush in at like a fraction of the speed of light. They hit that impossibly dense core and rebound in a catastrophic shockwave.
Okay, so that blast blows the outer envelope into space as this phenomenally hot, expanding cloud of ionized gas.
Yep.
And it leaves behind, what, a city-sized neutron star or a black hole in the center?
Exactly. And we understand that baseline. I mean, it's violent, it's incredibly bright, and it leaves behind extreme remnants.
But SN 2017 Gemeter throws a massive wrench into those standard calculations.
A massive wrench. I mean, this wrench really emerged as a full-blown crisis in astrophysics over the last couple of decades.
Really? A crisis?
No. Oh, yeah. As automated sky surveys got better, we started cataloging transients that just didn't make any sense.
Transients being these temporary bright flashes.
Right. And astronomers have identified nearly 400 of these exceptional core collapse events that simply do not fit the established math of a standard implosion rebound shockwave.
Okay.
We call them superluminous supernovae because they produce 10, sometimes up to 100 times the amount of visible light normally seen in a standard core collapse.
Okay, hold on. Let's unpack this physics for a second, because this is where my brain gets stuck.
Sure.
A star only has so much mass, right? Which means it only possesses a finite amount of gravitational potential energy.
That's basic thermodynamics, yeah.
So when it collapses, that potential energy is converted into the kinetic energy of the explosion and the thermal energy that produces the light we see.
Right.
So if the core collapse process is exactly the same, how can it suddenly generate 10 times more optical luminosity?
That's the million-dollar question.
Because you can't just spawn energy out of nowhere. The ledger has to balance.
Yeah.
If a regular supernova is like a stick of dynamite, this superluminous one is like a nuclear bomb. Where is the extra energy coming from?
Well, you've hit on the exact thermodynamic nightmare that theorists have wrestled with for years.
So I'm not crazy.
Not at all. The standard collapse model provides a very specific energy budget, typically around 10 to the 51 ergs of kinetic energy.
10 to the 51 ergs.
Right, a unit astrophysicists often call a FOE or a beef.
A FOE, F-O-E.
Yeah, it stands for 10 to the power of 51 ergs, F-O-E.
Ah, okay. Clever.
Very clever. But when you measure the light curve of a superluminous supernova, the optical energy being radiated away far exceeds the total available thermal energy from a standard shockwave.
It's just too bright for too long.
Exactly. The math bluntly indicates a missing energy source.
Like a massive gaping hole in the energy ledger.
Precisely. And because the laws of thermodynamics demand that the energy has to come from somewhere.
This can't just be magic.
Right, no magic in astrophysics. Theorists deduce there must be a hidden power source, a secondary central engine operating inside the explosion long after the initial collapse.
Okay, so something buried deep within that expanding cloud of stellar debris that is continuously injecting massive amounts of fresh energy into the supernova.
Exactly. And to find that missing energy, we have to look at the crushed core left behind.
Remnant.
Right. If a standard supernova leaves behind a standard neutron star.
Which is already crazy, packing the mass of a sun into a sphere 10 miles across.
Right, already extreme. But the engine we are looking for has to be an even more extreme variant.
Okay.
We're looking at the formation of a magnetar.
A magnetar. Just the name sounds intimidating.
It is. The magnetar hypothesis became the leading candidate to solve this energy crisis.
So what exactly makes it different from a normal neutron star?
Well, a magnetar is a neutron star, but it possesses the strongest magnetic fields known to exist in the universe.
Wow.
And understanding the scale of its magnetism requires stepping far, far outside of everyday physics.
Okay, give us a sense of that scale. Because a standard neutron star already has a magnetic field, what, millions of times stronger than Earth's?
Yeah, easily. But a magnetar's magnetic field is up to 1,000 times the intensity of a typical neutron star.
1,000 times stronger.
We are talking about magnetic field strengths on the order of 10 to the 15 Gauss.
10 to the 15 Gauss?
Yes, and to put that in perspective, it is 10 trillion times stronger than a standard refrigerator magnet.
10 trillion. Okay, wait. Let's really visualize this.
Here.
If you had a magnetar located halfway between Earth and the moon.
Okay, so roughly 120,000 miles away.
Right, a huge distance. Its magnetic field is so intense it would, wipe the data from every single credit card on our planet?
Oh, absolutely. And it would do a lot worse than that.
Like what?
It would literally warp the electron clouds of the atoms in your body, stretching them into tiny cigars.
Wait, really? It changes the shape of atoms?
Yes. It is a level of magnetic violence that fundamentally breaks the rules of chemistry.
That is terrifying.
It really is. It is an environment where the vacuum of space itself becomes unstable.
Wow.
But here's the catch. The static magnetic field alone isn't the engine.
It's not enough to just be a strong magnet.
Right. The engine requires motion. When this city-sized supermagnetic object is born in the immediate aftermath of the core collapse, it is not sitting still.
Right, because if you take a stellar core the size of the Earth and violently crush it down to the size of a city, conservation of angular momentum dictates it has to spin up.
Exactly. It's the classic figure skater analogy.
The skater pulls their arms in and their rotation accelerates drastically.
Spot on. On a cosmic scale, that means this hyperdense core is rotating at a terrifying speed.
How fast are we talking?
We expect a newly formed magnetar to rotate with a period of roughly 1 millisecond.
1 millisecond?
That means an object with more mass than our entire solar system, packed into a sphere the size of Manhattan, is spinning on its axis 1,000 times every single second.
1,000 times a second? That is absurd.
It strains credulity, but the math holds up.
Let's look at the Crab Nebula to anchor this, because I think that helps.
Okay, good comparison.
So the Crab Nebula was formed from a supernova observed by Chinese astronomers back in the year 1054, right?
Correct.
And today, the isolated neutron star at its heart, the Crab pulsar, spins about 30 times a second.
Sweeping a lighthouse beam of radiation toward Earth. Exactly.
And then 30 times a second is already mind-boggling for something that heavy.
Right. And our newborn magnetar is spinning over 30 times faster than the Crab pulsar while possessing a magnetic field vastly stronger.
So it's just on a completely different level.
Exactly. The combination of that extreme millisecond rotation and that phenomenal 10 to the 15 Gauss magnetic field acts as a colossal unipolar inductor.
An inductor, so it's a cosmic dynamo.
A gigantic electrical generator.
But wait, I have a question about that.
Go for it.
If the magnetic field is that strong and it's interacting with the surrounding environment, shouldn't that act as a massive brake? Because magnetic braking is a known phenomenon. Shouldn't it just violently arrest the rotation almost immediately? How does it sustain the power output for months to power a supernova?
That is a brilliant question. And the answer is, it does act as a brake?
It does.
Yes. That is the very mechanism of the engine.
Oh, I see.
The magnetic field drags against the surrounding plasma, and in doing so, it acts to slow down the star's spin.
Okay.
But because the magnetar has so much mass, its rotational kinetic energy is astronomically huge.
It has so much inertia.
Exactly. As the magnetic braking slows the spin, that immense reservoir of rotational energy doesn't just disappear.
Thermodynamics again. It has to go somewhere.
Right. It is violently bled off and transferred outward. The braking is the energy transfer.
Wow.
It is tapping into the rotational inertia of the spinning star and converting it into an outward electromagnetic wind.
So the rotational kinetic energy of the star is physically extracted by the magnetic field and dumped into the surrounding environment. And that solves the energy budget problem. We have a power plant capable of generating the missing energy.
We do.
But here is the hurdle, and this is where I get confused again.
Okay, where's the disconnect?
How does a spinning magnet create the blinding visible light we see from Earth? Like, we have an engine, but how does the engine turn on the headlights?
Right, getting from a magnetic field to visible photon.
Exactly.
To cross that bridge, we have to move into intense particle physics.
Okay, buckle up.
We have to examine the space immediately surrounding that spinning magnetar. Which brings us to a theoretical framework pioneered by astrophysicists Indrik Verm at the University of Tartu and Brian Metzger at Columbia University.
Verm and Metzger.
Right. They mapped out the radiative transfer problem.
Yeah.
Basically how the energy from the magnetar moves outward and interacts with the expanding supernova debris.
Because the magnetar isn't sitting in a vacuum, right? It is trapped deep inside the massive expanding guts of the dead star.
Exactly. It's smothered in plasma. The rapid rotation of the magnetar, whipping that immense magnetic field through space, creates an induced electric field.
Okay, moving magnets create electric fields. That's basic physics.
Right. But this electric field is so powerful that it actually exceeds a threshold known as the Schwinger limit.
The Schwinger limit. Okay, I've heard this term, but this is where quantum electrodynamics gets incredibly strange, isn't it?
Very strange. The Schwinger limit is the point where the electric field is so strong, it literally tears the vacuum of space apart.
Wait, tears empty space apart? How do you tear nothing?
Well, in quantum mechanics, empty space isn't empty.
Right, it's boiling with virtual particles popping in and out of existence.
Exactly. The magnetar's induced electric field is so monstrous, it imparts enough energy to these virtual particles to make them real.
Oh, wow.
It rips electrons and their antimatter counterparts, positrons, straight out of the vacuum.
So let me get this straight. The magnetar is manifesting matter and antimatter out of empty space just by spinning.
Just by spinning. It is a continuous, massive outflow of pair creation.
That is insane.
It really is. And this outflow forms an enormous, highly pressurized bubble of relativistic particles surrounding the magnetar.
Okay, and we call this bubble.
We call this a magnetar wind nebula.
A magnetar wind nebula.
Yes. And within this extreme environment, the most critical interaction is annihilation.
Matter and antimatter colliding.
Exactly. When an electron and a positron collide, they annihilate, transforming their entire mass into pure energy.
E equals mc squared in action.
In its purest form. And specifically, they produce a pair of extremely high-energy gamma-ray photons.
Gamma rays.
Right. And simultaneously, two gamma rays can collide with enough energy to spontaneously produce an electron-positron pair.
So it goes both ways.
Yes, it is a chaotic churning factory, constantly creating and absorbing the most energetic form of light in the universe.
But wait, gamma rays are the highest energy light on the electromagnetic spectrum, right?
Yes, they are.
But they are completely invisible to the human eye.
They are.
So if this factory is churning out invisible high-energy radiation, how does this explain why the supernova is outshining its host galaxy in optical visible light?
And that is where the Vermetzger model comes in. It hinges on a process called reprocessing.
Reprocessing.
Yes. Those newly forged gamma rays do not simply fly off into space.
Right, because of the debris.
Exactly. They are completely boxed in by the expanding debris of the dead star. It's a massive shell of hot, dense, ionized gas, mostly composed of hydrogen and helium from the star's outer envelope.
But wait, if you're continuously injecting massive amounts of gamma ray energy into the inside of a dense shell of gas, wouldn't that immense radiation pressure just blast the shell apart? Like, why doesn't it just blow the envelope to shreds rather than downshifting the light?
That is a great point, and that is exactly what happens on a structural level.
Oh, it does?
Yes.
Yes.
The energy injection does accelerate the expansion of the ejecta, pushing it to higher and higher velocities.
Oh.
But crucially, as it pushes, the radiation interacts with the matter. The gamma rays cannot punch straight through because the density of the gas makes it entirely opaque to high-energy photons at this stage.
I see. It's opaque, so it's like turning on a phenomenally powerful searchlight inside a really thick fog bank.
I love that analogy. Yes.
The light doesn't just cut a clean beam through the fog. The photons hit the microscopic water droplets. They scatter, they bounce around, and eventually the entire fog bank begins to glow from within.
That is incredibly apt. In astrophysics, this scattering is primarily dominated by a process called Compton scattering.
Compton scattering.
Right. The gamma-ray photons collide with free electrons in the ionized gas. And with every single collision, the gamma-ray loses a fraction of its energy.
And transfers it to the electron.
Exactly, which heats the plasma. The photon basically bounces around in a random walk, scattering millions of times, losing a little bit of energy with every single bounce.
So the extreme high energy of the gamma ray is slowly chipped away. It's downshifted.
The energy cascades down the electromagnetic spectrum. The invisible high-energy gamma rays thermalize the plasma, heating it up so intensely that the gas itself radiates that energy away as lower-energy optical and ultraviolet light.
Wow.
So the invisible blowtorch of the Magnetar wind nebula pumps its energy into the surrounding gas, forcing that massive envelope to glow with an intensity it could never achieve purely from the initial explosive shockwave.
That is brilliant.
This reprocessing is the precise mechanism that makes it a superluminous supernova.
The chain of causality there is staggering. Like, a core collapses, physics forces it to spin at millisecond speeds.
Right.
The rotation and immense magnetic field tear the quantum vacuum apart to create an antimatter wind.
Yep.
The antimatter annihilates into gamma rays. The gamma rays get trapped in the expanding stellar guts. They bounce around, lose their energy, heat the gas, and force the entire explosion to shine 10 times brighter invisible light.
It is an incredibly elegant theoretical framework.
It really is.
And, you know, for nearly 20 years, the Magnetar model was just that.
It's just a theory.
A brilliant, mathematically sound theory, yes. It beautifully solved the thermodynamic crisis of the superluminous supernova.
But it remained frustratingly unproven.
Exactly.
Because seeing the visible light isn't enough, right?
No, it's not.
The visible light just tells you the fog bank is glowing. To prove the theory, you need to see the searchlight itself.
Right.
You need direct observational evidence of the gamma rays.
And that proved to be incredibly difficult. Astronomers spent 2 decades searching through archival data from thousands of supernovae.
Thousands of them.
Thousands, looking for a high-energy gamma-ray signal that would definitively prove the existence of this central engine. And for 20 years, they found only tantalizing hints.
Really? Why was it so difficult to find? I mean, if these things are outputting that much energy, shouldn't they light up gamma ray detectors like a Christmas tree?
You would think so, but the difficulty stems from 2 massive observational hurdles.
Okay, what's the first one?
First, superluminous supernovae are exceedingly rare.
Oh.
And consequently, they typically occur at extreme cosmological distances, like often billions of light years away.
And distance is a problem for gamma rays.
Yes, because gamma rays from those distances are heavily attenuated by interacting with the extragalactic background light.
So they basically get absorbed or scattered before they even reach us.
Exactly. And second, and this is perhaps more importantly, as we just established with the reprocessing model, the gamma rays are initially trapped inside the dense ejecta.
Ah, the fog bank is too thick.
Exactly.
And by the time the fog clears and thins out, the engine might have spun down so much that the gamma rays are just too weak to detect from Earth.
You nailed it. You need a highly specific, almost perfect set of circumstances.
Okay.
You need a superluminous supernova that is unusually close to our galaxy, and you need to monitor it with highly sensitive instruments at exactly the right moment when the opacity drops.
When the fog lifts.
Right.
Which brings us to the recent hunt, the investigation that finally provided the definitive proof.
Finally. The breakthrough was achieved by an international team of researchers analyzing data from NASA's Fermi Gamma-ray Space Telescope.
Fermi.
Yes. Fermi is a phenomenal observatory launched in 2008, and it was designed specifically to monitor the cosmos for the most extreme high-energy events.
We should detail how Fermi actually catches a gamma ray, because it's not like a traditional optical telescope with, like, a glass mirror, right?
Oh, not at all.
You can't reflect a high-energy gamma ray. It'll just blast straight through a mirror.
Exactly. You're touching on the fundamental engineering challenge of high-energy astrophysics.
How do you catch a bullet made of light?
Right. Fermi's primary instrument, the Large Area Telescope, or LAT,
okay.
it relies on particle physics to detect light. It uses layers of silicon strip detectors interleaved with ultra-thin foils of tungsten.
Tungsten.
Yes. When a high-energy gamma ray enters the telescope, it hits an atom in the tungsten foil, and the impact forces the photon to undergo pair conversion.
Meaning?
It spontaneously transforms into an electron and a positron.
Wait, really? It uses the exact same pair creation physics that the Magnetar uses, just in reverse.
Exactly. It's poetic, really. Those newly created charged particles then travel through the silicon strips, leaving a measurable electrical trail.
Okay, so it tracks the particles.
Right. By tracking the path of the electron and positron, the onboard computers can calculate the exact trajectory and energy of the original gamma ray that created them.
That is a masterpiece of instrumentation.
It really is.
Yeah.
So, equipped with Fermi's historical data, the research team, which was led by Guillem Martí de Vesa.
He's a fellow at the Institute of Space Sciences in Barcelona, right?
Yes. They decided to initiate a highly focused search. Instead of looking at every distant supernova, they narrowed their parameters significantly.
Smart. So what did they focus on?
They concentrated their analysis specifically on the 6 nearest superluminous supernovae that had detonated during the first 16 years of the Fermi mission's operational lifespan.
Okay, so they were hunting for the most statistically viable candidates, the closest ones. And the impetus for this specific targeted hunt actually originated a little earlier, right? There was like a clue in 2024.
You're right. The groundwork was laid by a study led by Li Shang at Anhui University in China.
Okay.
They were combing through archival Fermi LAT data and noted a subthreshold signal.
A subthreshold signal, so not a confirmed detection.
Right. It was a hint that Fermi might have caught a marginal glimpse of gamma ray emission from an older superluminous event.
It wasn't the definitive, 5 sigma statistical certainty you need for a firm discovery.
No, but it was enough to alert the community that the signal might be hiding in the noise.
It's like smelling smoke and knowing there's a fire somewhere.
Exactly. It provided the necessary motivation for Martí de Vesa's team to execute a much deeper, more rigorous statistical analysis of the nearest candidates.
And out of those 6 supernovae surveyed,
only one yielded the incontrovertible smoking gun.
ESET 2017 UMARE.
Yes.
Our supernova sitting 440 million light-years away in Ursa Major.
SN 2017 Gamma ray showed definitive evidence of gamma rays. For the very first time in the history of astronomy, researchers had clear, unambiguous proof confirming the 20-year-old theory.
That some supernovae are indeed powered by central engines that emit staggering amounts of high-energy gamma rays.
They found the pulse of the Magnetar.
That's amazing. But, the simple detection of the gamma rays isn't even the most compelling part of this discovery, in my opinion. No, it is the timeline, the timing of when the gamma rays arrived at Earth relative to the visible optical light.
Oh, absolutely.
Yeah.
The timeline analysis is what transforms this from a great observation into a profound validation of theoretical physics.
Right.
The analysis of the temporal data was led by Fabio Assaro at the University of Paris-Saclay.
Okay.
And when they correlated the Fermi Gamma-ray data with the optical light curves recorded by ground-based telescopes, they observed exactly what Verm and Metzger had mathematically predicted years earlier.
Which was what?
The gamma rays did not arrive at the same time as the initial flash of visible light.
Right. The optical light, the visible explosion, was cataloged on May 23, 2017.
Yes.
But Fermi didn't see the gamma rays on May 23.
No, there was a significant prolonged delay. Fermi did not detect the high-energy signal until approximately 3 months after the initial core collapse.
3 months.
3 months.
I just want to emphasize that. For a quarter of a year, this exploding star is shining with the brilliance of hundreds of billions of suns in visible light,
Right.
but it is completely, totally dark in gamma rays. And then suddenly, the high-energy signal turns on.
Yep.
Explain the mechanics of that delay. Why exactly 3 months?
It comes right back to the opacity of the expanding debris, the thickness of our cosmic fog bank.
Okay, the searchlight in the fog.
Exactly. In the immediate aftermath of the explosion, the ejecta is incredibly dense. The Magnetar is churning out gamma rays, but every single photon is undergoing relentless Compton scattering.
Bouncing around.
They're all being absorbed, downshifted, and reprocessed into the optical light we see. The system is optically thick to gamma radiation.
So none of the primary gamma rays can escape the trap.
Not a single one. But the supernova debris is not static. It is expanding outward into space at thousands of kilometers per second.
All right, it's an explosion.
And as the volume of the debris shell increases, its overall density must decrease. The gas is thinning out.
The physical space between the atoms and the gas is growing larger, meaning a photon has a higher probability of traveling further without hitting an electron.
Exactly. The opacity drops over time. And roughly 3 months after the initial collapse, the expanding ejecta reached a critical threshold.
It became transparent enough.
Yes. The fog thinned out just enough that the gamma rays produced by the central Magnetar wind nebula were no longer entirely trapped and downshifted.
Wow.
A fraction of them could finally punch through the thinning veil without interacting with the gas.
They broke out of the envelope, traveled unimpeded across 440 million light-years of intergalactic space, and hit the tungsten foils inside the Fermi telescope.
It is a phenomenal confirmation. To construct an abstract mathematical model involving quantum vacuum breakdown, magnetic unipolar inductors, and complex radiative transfer equations.
Right. All just math on a chalkboard.
And then to observe the universe, execute that exact physical sequence with a perfectly timed 3-month delay. I mean, it is a triumph of the scientific method.
It proves we aren't just making educated guesses about the night sky anymore. We are literally watching the internal gears of the universe turning in real time.
We really are.
But, as is the nature of observational astrophysics, answering a 20-year-old question immediately introduces a host of new anomalies, right?
Of course. It never ends.
The universe rarely hands over all the variables in a clean package.
No. And the late-time behavior of SN 2017 Ravemeter ensures theorists will stay busy for a long time.
Because while the initial superluminous blast and the subsequent 3-month gamma-ray breakout beautifully align with the pure Magnetar wind nebula model.
The extended observation of the star's fade-out presents significant complexities.
Okay, so what happens as the supernova ages? I mean, it obviously has to fade eventually as the Magnetar spins down and loses energy.
Right, the magnetic braking slows it down.
But you're saying it didn't fade according to the mathematical script?
No, it didn't.
Yeah.
The researchers, including Fabio Assaro, conducted long-term tracking of the event's luminosity.
Over years, you mean?
Over years, yes. A pure Magnetar model, where the energy output is strictly governed by the magnetic braking of the star's rotation, predicts a very smooth, continuous, predictable decline in light over time.
Like a spinning top slowly losing momentum.
Exactly. But the later stages of SN 2017 GEM's optical fade-out were irregular.
Irregular how?
The luminosity fluctuated. It exhibited bumps and deviations from the expected decay curve.
Oh, so the engine isn't just smoothly running out of gas.
No.
It's sputtering, or there are other energy sources entirely that are polluting the data.
Exactly.
So what are the alternative physical processes that scientists suspect are complicating this long fade-out?
Well, the consensus is that the Magnetar engine is undeniably the primary driver. But at late times, secondary contributing factors begin to assert themselves.
Okay, what's the first one?
One major physical mechanism suspected to be at play is known as fallback accretion.
Fallback, meaning parts of the exploding star never actually managed to escape the gravitational pull of the core.
Precisely. The initial shock wave is immensely powerful, accelerating the star's outer layers outward.
Right.
However, the newborn magnetar sitting in the center still possesses an immense gravitational field.
It is the mass of a sun, after all.
Right. So the innermost layers of the stellar envelope, the material closest to the core, might not achieve the necessary escape velocity.
It gets launched, but not fast enough.
Exactly. As the initial explosive kinetic energy dissipates, this inner material stalls, reverses direction, and falls back inward,
Plunging toward the surface of the rapidly spinning magnetar.
Yeah.
And dropping millions of tons of superheated plasma onto a highly magnetic, rapidly spinning city-sized neutron star that has to release a staggering amount of energy.
All the material possesses immense gravitational potential energy. As it falls back and impacts the magnetar or interacts with the intense magnetic field lines, it converts that potential energy into severe bursts of high-energy radiation.
Bursts, not a steady stream.
Right. This fallback accretion is highly chaotic and episodic. It does not provide a smooth, continuous energy injection like the rotational dynamo.
Which would perfectly explain the irregular, bumpy fluctuations seen in the late-time optical light curve.
Exactly. It adds significant noise to the underlying signal.
That paints a picture of extreme violence, just gravity clawing back the debris of the explosion, creating secondary flares.
It's a messy process.
What is the other leading possibility for the irregular fade-out?
The other highly significant factor involves the macroscopic environment surrounding the star before it even died.
Before it died.
Yes. We refer to this as circumstellar interaction, or CSI. The core collapse supernova shockwave doesn't merely expand into a pristine empty vacuum. It expands into the medium modified by the progenitor star.
Modified how? Massive stars don't just sit peacefully until they explode, do they?
Far from it. The most massive stars in the universe, particularly those classified as luminous blue variables or Wolf-Rayet stars.
The real giants.
Right. They are highly unstable in the final evolutionary stages of their lives. In the centuries, millennia, or even just decades prior to their ultimate demise, they suffer massive, eruptive, mass loss events.
Mass loss events.
Driven by intense radiation pressure or instabilities in their outer envelopes, they literally shed huge fractions of their own mass,
Wow.
blowing enormous shells of dense gas out into the surrounding stellar neighborhood.
So the star is essentially coughing violently, burping out massive, thick rings of its own atmosphere long before the final catastrophic core collapse.
That's a great way to put it. When the core finally does collapse and the main supernova blast wave accelerates outward at a fraction of the speed of light,
it inevitably slams into those pre-existing, slower-moving shells of material.
Yes.
It hits cosmic speed bumps.
Huge speed bumps, and the collision is incredibly violent. The blast wave drives a forward shock into the dense circumstellar material and a reverse shock back into the supernova ejecta.
Oh, man.
The kinetic energy of that collision is thermalized, generating massive amounts of visible light and high-energy X-rays and gamma rays.
But this emission is entirely distinct from the central magnetar engine, right?
Completely distinct. It is purely the result of the outer blast wave plowing into the ancient debris field of the dying star.
So the irregular, bumpy fade-out we see years after the initial explosion might actually be the blast wave hitting these concentric shells of gas that the star laid down hundreds of years ago.
Exactly.
We are seeing the geographic history of the star's final centuries written in the shock wave.
It is highly probable that what we are observing in the late stages of SN 2017 Jamity is a complex, turbulent confluence of all these phenomena.
The underlying magnetar engine slowly running down.
Chaotic clumps of material falling back onto the core.
And the outermost blast wave violently interacting with a messy, complex, circumstellar environment.
It reveals that stellar death is not a clean, singular event, but a chaotic, prolonged process.
Despite the messiness of the late-stage data, the detection of those initial delayed gamma rays remains a watershed moment for the field.
Assalamualaikum.
We have finally pulled back the curtain on the engine room.
The impact on the astrophysical community is profound. Manos Chatsopoulos, an associate professor in LSU's Department of Physics and Astronomy, was deeply involved in evaluating the viability of these competing theoretical models.
What did he have to say about it?
He articulates that detecting gamma rays gives us a direct, unadulterated probe into the central engine. We're no longer solely reliant on observing the downshifted, reprocessed optical light of the glowing debris.
Right.
We're seeing the high-energy signature of the central power plant itself.
It's the difference between seeing a glowing lampshade and directly measuring the filament inside the bulb.
That is exactly it. And Judy Racusin, a deputy project scientist for the Fermi mission at NASA Goddard, has similarly emphasized the paradigm-shifting nature of this event.
How so?
She points out that observing gamma rays from supernovae provides a totally new methodology to explore their inner workings, building upon 2 decades of slow theoretical advances.
And as Chathopoulos noted, the models have predicted for years that this high-energy emission would eventually emerge once the ejecta became optically thin. But until SN 2017 Gamma-ray, we simply lacked an event that was close enough, bright enough, and observed with sufficient long-term continuity to prove it definitively.
It was the perfect storm.
This detection stands as the clearest evidence yet that we are directly observing the relativistic mechanics of a magnetar-powered explosion in action.
It really does.
But, the reality of science is that one definitive detection, while groundbreaking, it's just a sample size of one.
Always the caveat.
Right. We need a population. How do we turn this single event into a robust statistical understanding of the universe? If these explosions are so far away and the gamma rays are so hard to detect, where do we go from here?
We look to the future of instrumentation. The researchers are already actively planning observation strategies utilizing the next generation of observatories.
Like what?
Specifically, the team examined how a new, highly advanced ground-based facility called the Cherenkov Telescope Array Observatory, or CTAO, will fundamentally alter the landscape of high-energy astronomy.
Okay, let's clarify something crucial here.
Sure.
You just mentioned a ground-based facility for gamma-ray astronomy.
Yes.
But earlier we established that Earth's atmosphere is totally opaque to high-energy gamma rays, which is exactly why NASA had to put the Fermi telescope into orbit in the first place.
Right, to get above the atmosphere.
So how can a telescope sitting on the ground observe gamma rays that never reach the surface?
It is a brilliant workaround that relies on the atmosphere not as a shield, but as the detector itself.
The atmosphere is the detector.
Yes. It is true that the primary high-energy gamma ray from a distant supernova does not reach the ground. But when a gamma ray possessing immense energy, and we're talking tera-electron volts here.
Huge energy.
Huge. When it slams into the upper atmosphere, it interacts with the nucleus of an atmospheric molecule, like nitrogen or oxygen.
A microscopic collision high in the stratosphere.
Exactly. And that collision initiates a catastrophic cascade. The primary gamma ray converts into an electron-positron pair.
More pair creation.
Yes. And these particles then emit more gamma rays via a process called Bremsstrahlung, or braking radiation.
Braking radiation, okay.
Which in turn create more electron-positron pairs. This creates an extensive air shower, a microscopic avalanche of millions of secondary subatomic particles raining down through the atmosphere.
An avalanche of radiation.
Crucially, these secondary particles are traveling with immense kinetic energy. In fact, they are traveling through the atmosphere faster than the local speed of light in air.
Wait. I need to stop you there.
I knew you would.
Nothing travels faster than the speed of light. That's the fundamental speed limit of the universe.
Nothing travels faster than the speed of light in a perfect vacuum, which is roughly 300,000 kilometers per second.
Okay.
However, light slows down when it travels through a medium, like water or air.
Oh.
So the speed of light in air is slightly slower than the absolute universal speed limit.
Okay, that makes sense.
And the high-energy particles in the air shower are moving faster than that reduced local speed limit.
That makes perfect sense. It's like a supersonic jet breaking the sound barrier, but for light.
That is exactly what it is.
Yeah.
And just as a jet breaking the sound barrier creates a sonic boom, these particles breaking the local optical speed limit create an optical boom.
An optical boom.
Yes. They emit a faint, incredibly brief, bluish flash of light known as Cherenkov radiation.
Cherenkov radiation.
The flash lasts for only a few billionths of a second.
And that is what the ground-based telescopes are looking for.
Exactly.
They aren't looking directly at the supernova. They are staring at the dark sky, waiting for the atmosphere to flash blue.
You've got it. The Cherenkov Telescope Array utilizes dozens of massive, highly sensitive dish antennas scattered across huge areas of land.
Right.
When an air shower occurs, these telescopes catch that fleeting nanosecond flash of Cherenkov radiation. By analyzing the shape, timing, and intensity of the flash across multiple telescopes, supercomputers can geometrically reconstruct the entire air shower backward
To find the source.
determining the exact energy and trajectory of the original primary gamma ray that struck the top of the atmosphere.
Using the Earth's atmosphere as a giant calorimeter, that is engineering genius.
It's beautiful.
And how much more capable will the CTA be compared to our current space-based instruments?
The leap in sensitivity is staggering. The research team calculates that with just 50 hours of dedicated observation time, the Cherenkov Telescope Array Observatory could detect high-energy events similar to SN 2017 GA-mator at distances up to 500 million light-years away.
Wow, that pushes our sensory boundary vastly further out into the cosmos, capturing a much larger volume of space.
Which exponentially increases the statistical likelihood of catching these rare superluminous events right as the optical fog clears.
That is incredible.
And as Michela Negro, an assistant professor at LSU and a prominent member of the Fermi Large Area Telescope collaboration, emphasizes, the true power of this new era will not rely on a single instrument. The future of high-energy astrophysics hinges on multi-messenger coordination.
Working together.
Exactly. The greatest leaps in understanding will emerge from the real-time cooperation between these new high-sensitivity ground facilities like CTA and the established space fleets like NASA's Fermi and Swift observatories.
It signifies a major philosophical shift in how we observe the universe, doesn't it?
It really does.
We are moving away from simply taking long-exposure photographs of static skies. We are operating a coordinated, real-time diagnostic network, triggering different instruments across the globe and in orbit to watch a single catastrophic event unfold across every frequency of the electromagnetic spectrum.
And what is truly fascinating here is the arc of scientific progress we have traversed.
Definitely.
For 20 years, the superluminous supernova central engine was confined to theoretical mathematics written on chalkboards and simulated on supercomputers.
It was an abstract concept.
Exactly. Then, through rigorous observation and technological innovation, one definitive detection takes that abstract math and materializes it into a physical, observable reality.
It takes the hypothetical and makes it concrete.
It doesn't just solve an old thermodynamic problem. It establishes an entirely new subfield of time-domain astronomy. We are entering an era where we don't merely measure the secondary light of an expanding debris field. We are utilizing multi-wavelength observatories to peer straight through the wreckage, looking directly into the roaring magnetic heart of the dying star.
It is a completely new window into the extreme physics of the universe.
It is.
So, to synthesize this incredible journey we've mapped out today,
A long journey.
a very long journey, we began with a massive star, bloated and unstable, reaching the absolute end of its evolutionary timeline. The delicate equilibrium between fusion and gravity fails.
Right.
The core collapses in a fraction of a second, crushing down into a magnetar, a violently spinning, hyperdense core the size of a city, possessing a magnetic field 10 trillion times stronger than a household magnet.
It's still hard to fathom.
The extreme physics of this object tear the quantum vacuum apart, churning out a wind of antimatter that annihilates into highly energetic gamma rays.
Which is the hidden engine.
Exactly, and those gamma rays are initially trapped inside the expanding guts of the dead star. They bounce around the dense plasma, acting like a cosmic blowtorch inside a thick fog bank.
Downshifting the light.
The gamma rays lose their high energy, heating the gas and downshifting into visible light. This hidden reprocessing mechanism forces the explosion to glow with the optical intensity of 10 normal supernovae, creating a superluminous event that outshines entire galaxies.
And finally, months later, as the supernova debris expands into the void and its density drops.
The cosmic fog lifts.
Yes.
The original gamma rays from the central engine finally leak out, travel across 440 million light-years of space, and strike our instruments, definitively proving the existence of the engine.
It is a flawless, beautiful narrative of discovery.
It is.
Yeah.
But before we conclude, I want to leave you with one final thought to ponder. Something that pulls back from the particle physics and looks at the sheer terrifying majesty of what we are actually observing.
Okay, I'm listening.
Think about the timeline of the irregular optical fade-out we discussed. The idea that the outward blast wave of SN 2017 GA-mator might be violently colliding with massive shells of matter that the star had ejected centuries or even millennia before it finally died.
The circumstellar interaction. The geographic history of the star's mass loss.
Exactly. This implies something deeply profound about stellar evolution. It implies that these massive, universe-shaping stars do not merely die in a sudden, singular, instantaneous flash.
They don't just switch off.
They experience a prolonged, violent, chaotic agony. They are shedding pieces of themselves into the freezing void, convulsing and burping out their own atmospheres long before their final spectacular collapse.
The death of a star is an ongoing era, not a single timestamp.
Exactly. So when you go back outside tonight and you stand in the dark and you look up at the night sky, you aren't just seeing static points of light. You aren't looking at a frozen, peaceful picture. You are watching the slow, multi-generational breathing, convulsing, and dying of the cosmos. It is a continuous process of immense violence and creation, an intricate clockwork of gravity, magnetism, and quantum mechanics, all playing out on a timescale that utterly humbles the brief human experience.
It really puts things into perspective.
And to think we only grasp the depths of this violence because we finally learn how to build a machine sensitive enough to spot the invisible light leaking out from the engine of a broken star. The universe has always been broadcasting its secrets. We just finally learned how to tune the receiver.